Hi guys, welcome back. Let's see, the place that I wanted to start is just to give you guys a little bit of an overview and to review where we left off in our notes. The topic we were talking about was calorimetry, and I showed you guys this picture of a coffee cup with a thermometer inside. This is the setup that I want you to have in your brain when you're thinking about these calorimetry problems. Now, for this type of problem, we're assuming we have an isolated system. So we've got this really good styrofoam cup and no heat is escaping the styrofoam cup. What we're doing for these problems here is that we're going to measure the change in temperature inside the cup. So that's why you can see we always have a thermometer here because this is the measurement that we're doing. Once you get that change in temperature, it could be going up or it could be going down, inside your isolated system, we're going to do calculations to translate that in to how much heat is released or absorbed inside the cup. Now that heat gets the symbol Q, so we can calculate Q, and then we can also translate that Q into delta H, the enthalpy of the reaction. And as we're doing calculations, I'll be more specific about what is the difference between Q and delta H. But right now we're going to use them interchangeable. They sort of just mean how much heat was released or absorbed. Now we talked about types of calorimetry problems, and I want to go over that quick here as well. The first type of calorimetry problem, we did this in your notes, we did practice problems, so look at pages 124 to 125 in your supplement. This is where there's no reaction. So all you're doing is you have one pure substance inside your coffee cup, and oftentimes you're just heating it up. So you're going to heat it up, measure the final temperature, and you can calculate how much heat was absorbed in joules or kilojoules using our equations. This type of problem tends to be really straightforward. You just have one equation that you're plugging into and you're calculating how much heat was absorbed based on a temperature change of one pure substance. The one pure substance tends to be water. That's the thing we've got the specific heat capacity for. That's what we mostly do. Type 2. In the type 2 calorimetry problem, still you're not doing a chemical reaction, but you're taking two things and you're mixing them together inside your coffee cup. And the way I like to think about this is you've got a hot object with some high initial temperature and a cold object with some low initial temperature. You put those together in your little styrofoam coffee cup and they're going to hit the same final temperature somewhere in between. So I'm going to call that warm. You're still not doing a chemical reaction here, so there's no Q reaction term in your equations, but you're going to set all of the heat that's lost by the hot object, you're going to be setting that equal to all the heat that's absorbed by the cold object, because we're assuming that no heat is escaping from our amazing styrofoam cup. Lastly, the third type of calorimetry problem, this is where things start to get tricky, and this is where we left off in our notes, and this is what we're going to be doing next. I'll have another video in which I'm sort of walking you through a problem and showing you all the steps. But I want to be clear about how do I think about these types of problems. So I'm going to do a chemical reaction inside my coffee cup, and I'm going to measure the change in temperature. So let me walk you through, based on that change in temperature, what type of reaction am I talking about? So I'm talking about this third type of calorimetry problem where I have a chemical reaction. Just like before, I'm always measuring the change in temperature. That's the measurement that I'm taking away from these calorimetry experiments. And remember that delta T is always T final minus T initial. So whatever the temperature is at the end of the reaction minus whatever the temperature is at the beginning of the reaction. You could have a positive or a negative delta T, and that tells you about what type of reaction that you have. So first off, let's say you have a positive delta T. So you hit a higher final temperature. What that means is that you did a reaction inside your coffee cup that warmed up the solution so that you hit a higher final temperature. What you can say about that reaction, if delta T is positive, is the reaction must be exothermic. It's releasing heat and it's heating up the solution in your coffee cup. So just by knowing that delta T is positive, I know, oh, that reaction must be exothermic. It gave off heat that heated up the solution, which helped me reach a higher final temperature. If I have the opposite, if delta T is negative, so if it goes down in the course of the reaction, that means that the reaction itself is absorbing heat and taking it away from the solution, which makes my reaction endothermic. It's heat is going into my reaction, it's taking in heat and taking it away from the solution, which makes the temperature go down. Delta T is negative. So I'm going to stop this introduction here. This is where we're going to pick up in our notes, and I'm going to show you how do I do these types of calculations. I've measured delta T, I know what type of reaction I have, and now I'm going to start to do calculations where I set up all of my Q lost equals negative Q gain. So let me stop here and I'll pick it up in the next video.